Hey guys, chapter 2 still, organizing and summarizing data. This time we're going to talk about additional displays of quantitative data. Quantitative meaning quantity. So first thing we're going to talk about is the stem and leaf plot. So stem and leaf plot is another way to represent the quantitative data graphically in a stem and leaf or stem plot. So using the digits to the left of the rightmost digit of the stem, each rightmost digit forms a leaf. So it sounds kind of confusing, but we'll see this together. So for example, the data value 147 would have 14 as the stem and 7 as the leaf. So step 1, 7, or the stem for Alabama is 16, and the corresponding leaf, where were we? There we go. Okay, so the data in table 14 in the next slide represents the percentage of persons living in poverty by state and in 2017. So draw a stem and leaf plot of the data. So looking at this data here, it would be more realistic to use the decimal as a stem. The only thing we would have to do is actually show the scale. So looking at that, there we go. So the stem for Alabama is 16 and the corresponding leaf is 9. So we look at Alabama 16.9, 16 is the stem, 9 is the leaf. So instead of continuing on there, let's go ahead and get the, so let's get our data onto a table. So looking at this, we're going to start off with our lowest number. And the smallest number that we have here, I'm looking and I see a 9.6 right here, 9.5, 9.3 seems to be the smallest. 7, okay, 7.7. And there we go. So the smallest number we have is 7. The largest number we have, I'm seeing 19. Yep. So the smallest number we have is going to be 7. The largest number we have is going to be 19. So we're going to come over here and write these numbers. So 7 to 19. So 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19. So from here, now that we have those values, we, instead of writing tag marks, we're going to actually write the value that we have for the decimal place. So going here and looking at these values. Okay, so 16 and 9, 11, 1, 14, 9, 16, 4. And notice from here, what we're going to try to do is try to keep it a little bit more organized. So the first column here, second column here. So we're going to do a better job at trying to keep it more organized than we did with the dot plot. The last one we did was 16, 4, 13, 3, 10, 3, 9, 6, 13, 6, 16, 6. Let's fix this one. 16, 6, 14, 0, 14, 9, 9, 5, 12, 8, 12, 6, 13, 5, 10, 7, 11, 9, and going to the second column, 17, 2, 19, 7, 11, 1, 9, 3, 10, 5, 14, 2, 9, 5, 19, 8, 13, 4, 12, 5, 10, 8, 13, 0, 7, 7, 10, 0, 19, 7, 14, 1, 14, 7, and going up. So going up 10, 3, 14, 0, 15, 8, 13, 2, 12, 5, 11, 6, 15, 4, 13, 0, 15, 0, 14, 7, 9, 7, 11, 13, I'm sorry, 11, 11, 3, 11 or 10, 6, 11, 0, 19, 1, 11, 3, and 11, 3. So now from here, we have all the data represented here in that stem and leaf plot, but this isn't a formal stem and leaf plot just yet. What we have to do is put these in numerical order, and then it'll be a stem and leaf plot. So let's go ahead and take care of that. So starting off with 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19. So with each of these categories, what we're going to do is rewrite all of the values, but in numerical order. So with 7, we don't have to do too much because that one's already done for us. There's only one value there, so we don't have to put it in numerical order. With 8, we don't have any values here. So one thing we don't want to do is put a 0 here because a 0 is not going to, it doesn't represent 0. What this value represents is a value of 8.0, which is actually a value. So instead of putting a number there, we're just going to leave it blank. But now for 9, we could see that there's a couple of values, so let's put them in numerical order, with the smallest value being 3. So then we have 3, 5, 5, 6, and 9. So we have 1, 2, 3, 4, 5 numbers there. 1, 2, 3, 4, 5. Perfect. So now with 10, we're going to do the same thing there. But with 10, we have a couple of other values. So this one, we're starting off with 0. So we have 0. Do we have any 1s? No. 2, no. 3, we have 2 3s. 4, no, we have 1 5, we have 1 6, we have 1 7, and we have 1 8. So how many values do we have in each of them? So for 10, we have 1 2 3 4 5 6 7, 1 2 3 4 5 6 7. So we counted all of them. All right, next we're going to look for number 11, or row 11. Smallest value we have there is 0. Then we have 1, we have 2 1s. 2, no 2. 3, we have 3 3s. 2, 3. 4, we don't have any 4s, don't have any 5s. We have 6, 7, 8, and 9. Just to make sure, do we have all the numbers here? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. Now for 12. So for, or could I do this? There we go. All right, so for 12, we have 8, 6, 5, 5. So we have 5, 5, 6, 8. For 13, we have 3. Yep. For 13, we start off with 0. We have 2 zeros, 2, 3, 4, 5, and 6. We have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Perfect. For 14, we have 0. We have 2 zeros. 1. We have 1, 1. We have 1, 2. 3s, no. 4s, no. 5s, no. Next number is 7. We have 2 7s. And we have 2 9s. For number 15, we have 8, 4, 0. So we have 0, 4, and then 8. 16, 9, 4, 6. So that's going to be 4, 6, 9. For 17, we have 2. For 18, we don't have anything. For 19, we have 1, 7, 7, 8. And this time I made it a fact to put enough spacing so we could see where the numbers are separated for each of these. So it creates like these columns. And now without even graphing it, we kind of created our own distribution shape. So here we could see that majority of the data lies within these 2 values right here. And it kind of pops back up over here. So we would have like 2 different values right there. All right, and that's how we draw our stem and leaf plot. So let's see if we missed anything. Ooh, we have to talk about a legend. So 7 represents 7.7%. So that's the only thing that we forgot to do here. So 7, we could write the legend right down here. 7 given 7 is 7 or 0 point or 7.7. In this case, it's 7.7% because we're looking at the 2 different values here. And there we go. All right, so constructing the stem and leaf plot. So the stem of the data values will consist of the digits to the left of the rightmost value or the rightmost digit. The leaf of the data value will be the rightmost digit. So what they're kind of talking about with the stem and leaf, we're saying that this is the stem. So from the stem, we have all these tiny little leaves. So from this one, we have this value, this value, this value. It breaks up into those different leaves. Step 2, write the stems in the vertical column, increasing order, draw the vertical line right after the stem. 3, write each of the leaf corresponding to the stems to the right of the vertical line. 4, within each stem, rearrange the leaves in ascending order and title the plot and include the legend to indicate what the values represent. And here we're constructing a stem and leaf plot of the poverty data discussed in the previous example. So, 7%, we have 1 for, or I don't know what the left part is. Another way that you could rearrange it and give a legend is this, like leaf unit is 0.01. So telling us that this represents the 10th spot in the data values. And this is them writing everything on Minitab, but we're using Excel. So once a frequency distribution or histogram of continuous data is created, the raw data is lost unless reported with the frequency distribution. However, the raw data with the raw data from a stem and leaf plot, you could still retrieve it because you could see all of these values right here. The only thing you don't see is where these data came from. We talked about Alabama, I believe it was like 14.6%. So it would have been the 14 and, or was it 14.4? it was 16.4 or 16 or 16.9. Anyway, so you don't remember, you don't know exactly where that data came from, but you could still grab the raw data. You can't really grab the raw data from a histogram, especially like something like this. So here we don't have the raw data. With this one over here, we do have the raw data. Let's see. So a split stem and leaf plot, whenever we have rearranged these values to be a little bit too much, we could actually create a stem and leaf plot, like a double stem and leaf plot. So cutting everything in half. So what that would look like is us rearranging these data values. Okay, so the smallest data value has a 10 spot, the largest data value has a 4 spot. So here we could have we would have 1, 2, 3, 4, and just rearranging all of this. So we have 2, 7, 1, 3, 2, 3, 3, 2, 1, 8, 2, 4, 1, 8, 1, 5. And then continuing on from there. Okay, so 1, 7, 2, 9, 3, 0, 4, 8, 3, 2, 1, 5, 2, 1, 3, 7, then 1, 1, 2, 2, 1, 2, 1, 1, 2, 6, 1, 3, 2, 7, 1, 9, 2, 4, 1, 8. And see how we're kind of like losing our place here. We aren't going to be able to get to that many. We said 2, 4, 1, 8, 4, 6, 1, 8, 4, or 2, 4, 3, 1, 2, 0. Are we 1, 9, 3, 6, 1, 7. All right, 1, 7, 1, 7, 2, 3, 3, 8, 2, 2, 1, 6, 2, 9. So if you look at the data to the right, like this side, this one right here doesn't really give us much of a variability. So what we could do is rewrite all of this in like kind of doubling the columns. So starting off with 1, we could have 1, 1, then 2, 2, 3, 3, and lastly 4, 4. And this time organize the data to where it's going to fit and look a little bit nicer. So from here, let's look at all the values from 1 through 5, or 0 through 5, 0 through 4, and then 5 through 9. So 0, do we have any zeros? No, but we have 1, all the ones, 1, 1. And then 2s, we have 1, 2. Then 3s, we have 1, 2, 3s. All right, let's do this. So we had 1, 1, 2, 3, 3. No 4s, and that would cut off there. So we're cutting it off at 4 because we could break it up into 5 different possibilities for each. So this would be 0, 1, 2, 3, 4. And down here, we would have the possibilities for 5, 6, 7, 8, and 9. So 5 possibilities here, 5 possibilities here, and it's broken up perfectly. So that way we could look at these numbers like that. All right, so the next ones are going to be 5 through 9. So 5, we have 1, 2, 2 5s. Then 6s, we have 1, 6. 7s, we have 1, 2, 3 7s. 1, 2, 3. 8, we have 1, 2, 3, 4 8s. 1, 2, 3, 4. And 9s, we have 1, 2 9s. Then with 2s, we could do the same thing, starting off with 0. Do we have any zeros? We have 1 0. 1s, we have 1, 1 1. 2s, we have 1, 2 2s. 3, we have 1, 2 3s. 4s, we have 1, 2 4s. And 5 is going to belong to the next family. So with 5, we have no 5s. 6s, we have 1 6. 7s, we have 1 2 7s. 8s, no 8s. 9, we have 1 2 9s. Now looking at our 3s, we're going to write 0 through 4 in the first column or first row, 5 through 9 in the second row. So we have 1 0, 1 1, 1 2 2s, no 3s, and we have 1 4. 5 through 9 is going in the second column. So 5, no 6, we have 1 6. 7, we have 1 7. 8, we have 1 8. And that's it there. Then for 4, we don't have any 0 through 4 for 4s. And we just have 6 and 8. And there we go. That's how we're able to organize it. Now everything fits here. Over here just looks really crowded. It looks a little bit different, but here we could see the majority of the values come right here. And it does look a little bit more bell-shaped than we intended, right? So kind of, if you look there, more right skewed, but that's what the data looks like right there. So we were able to break it up a little bit better so we could see it a little bit nicer, see where majority of the data goes to. Next, constructing a frequency polygon. What we have here is like going back to our classes. So the class midpoint of the sum of the sum of the consecutive lower classes limits divided by 2. So the frequency polygon is a graph that uses points constructed by the line segments to represent the frequencies for the classes. It is constructed by plotting a point above each class midpoint on a horizontal axis at a height equal to the frequency of the class. Next, the line segments are drawn connecting consecutive points. 2 additional line segments are drawn connecting each of the ends of the graph to the horizontal axis. So graphing this just the same way we graphed it before. We have these values here. And let's see if we could have, oh, we don't have that. So what we did before, so remember our class limits went about like from here to here. They came up this way. So not like that. So our class limits were from here to here. I don't see it. All right. So There we go. So looking at this data table here, the way that we found our midpoint was adding these two values together and then dividing it by 2. So midpoint, we add the two values together, divided by 2. That's how we find the middle. If you guys remember that from like college algebra or intermediate algebra. But that's how you find the midpoint between 2 points, is you just add them together, divided by 2. And that's how we found this midpoint here. And that's how we went from there to this right here. So the midpoint ended up being this, telling us that the values that we originated with were 50 and 75. So 50 is about here, 75 is about here. So that means that our data came this way. There we go. And from, yeah. So from there, and then between 75 and 100, we add those two numbers together, divided by 2, that gave us 85. That's how we were able to find this point right here. That's what it was. That's why I keep getting confused, because that was 0 right there. And then from here to here, we're looking at these two values. It came up this high. And basically what we were looking for was the midpoint for those two values. So from here, the midpoint being drawn from one value to the next, there was a frequency of 1 within those two. And then between how do I get, there we go. So clearing that. So between these two values here, it was 1. Between these two values here, we had 0. Between these two values here, we had 7. And that's how we constructed these values over here. So 7 between those two values, 7 between 125 and 150. We had these two values right here. So we continue that on. Until we finish this graph. And it ends up looking, this graph in red represents what the bar graph looked like when we did graph it. So all we did was we grabbed the midpoints of those values and graphed them. So this one was another 0, this one here. The only thing that we did different here, let's draw the polygon here. So finding the midpoints and the height of each of these is what these dots represent. So each of these dots, we went the height that we did originally over here. So the height of 1, height of 0, height of 7. The only thing that we added to this graph were these endpoints. And the only reason we added those endpoints is to see where we ended up going with each of these. So starting off with 0, here we went up this far, we went down here, we went up this far, and we continue that all the way to the very last value where we ended up on the x-axis. So basically we start and we end in the exact same place. So now that we have that, we could also do that with the relative frequency. So remember, this is just regular frequency. We could do this with the relative frequency, dividing each of these values by the total number. So like dividing 13 by the total number of whatever it was earlier. But now with cumulative frequency, so with cumulative frequency, it's just a little bit different. A cumulative frequency distribution displays a aggregate frequency of the category. So in other words, for discrete data, it displays the total number of observations less than or equal to. So remember, we're always going to start with 0 and stop wherever it tells us to stop. We're adding all those values. We stop at the next value and add all those values. Stop at the next value and we're adding all those values. So starting at some point and telling it where to stop. So that's where we get our relative frequency. Kind of think of this class, whenever we end up with the final, it's an accumulative, it's the accumulation of everything that we learned in this semester. So that's what cumulative means. We're adding from the beginning up to that point. cumulative relative frequency. So let's break that up. So cumulative, add everything together, relative, the part of the whole, and then frequency distribution is just the way that we're organizing everything. So putting all of that together, cumulative relative frequency distribution displays the proportion or percentage of the observations less than or equal to the category for the discrete data, and the proportion or percentage of the observations less than or equal to the upper class limit for continuous data. So another cool thing, if we continuously start at 0 and tell it to stop right here, adding that, we add this, tell it to stop here. Once we get to the very end of the data set, we've accumulated all of the data. So we've accumulated 100% of the data. And remember, we're looking at relative frequency. Relative is just looking at the proportion that value holds. So cumulative relative frequency at the very end is holding 100% of the data. So it's like a little fun fact. All right, so looking at these values. So remember, we got our frequency by just doing little tally marks for everything. That's how we got that one. Relative frequency, we added all those values up together and then divided this number by that total. That's how we got the relative frequency. For cumulative frequency, we're just adding each value up. So here at the very first value, we only have 1. At the second value, we have 1 plus 0, so that gives us 1. For this next value, for cumulative frequency, we're adding all of these values up. So 1 plus 0 plus 7 gives us 8. Then adding the next one for this one. So 1 plus 0 plus 7 plus 10 gives us the 18 until we get down to the very last one. It gives us 50 because there were 50 different data values for that representation. And let's see. So now that's with cumulative frequency. With cumulative relative frequency, cumulative, we add everything up. Relative, it's that proportion of the whole. And frequency, we're just looking for the frequency of these. So instead of showing you all of that, so we could add these values together to get this, or we could just take this value and divide it by 50. So 27 divided by 50 gives us this value of 0.54. So now that we have those numbers, remember how I told you that at the very end, we end up with 100% of the data. If you multiply each of these numbers by 100, it gives you the percent. Multiplying this by 100 gives you 100%. So at the very end, the cumulative relative frequency is always going to be 100% of the data. And now constructing the frequency and relative frequency ogives. So ogive is a graph that represents the cumulative frequency or cumulative relative frequency for the class. It is constructed by plotting points whose x coordinates are the upper class limits and whose y coordinates are the cumulative relative frequencies or cumulative frequencies of the class. Then line segments are drawn connecting the consecutive points. In addition, line segment is drawn connecting the first point to the horizontal axis. So remember how earlier we had to do the first point to the horizontal axis, the last point to the horizontal axis. Here we don't really have that last point because the last point is going to be way at the top. It's going to be part of the 100%, especially with the cumulative relative frequency, 100%. And there you go. That's how you draw those there. So I believe this is the last graph. So the last graph that we're going to talk about is a time series graph. So if the value of a variable is measured at different points in time, the data are referred to as time series data. So a time series plot is obtained by plotting the time in which the variable is measured on the horizontal axis and the corresponding value of the variable on the vertical axis. The line segments are then drawn connecting the 2 points. Let's see. So looking at this data right here, let's go ahead and take this over to Excel. All right, so just like always, we're going to take a picture of the data. For me, it's Command-Shift-5 and cropping out the data capture, taking it over to Excel. And we are going to insert a new table, so data from table, from a picture. This one. All right, everything looks pretty good. We're going to insert data, even though there's a couple of mistakes that they think are mistakes. But from here, just like we have been doing, we're going to grab the data here and insert a graph. This time we're going to look at a time series graph, so a line graph. Let's see if they could recommend a better graph for us. There we go. From here, everything is organized for us. The smallest data value, or the smallest year is 2005, 2005 here, 2018 at the very end over here. Can make it look a little bit better. This one actually has the different values for each of those. And there we go. So let's see. It's exactly the same as it is in our slideshow if you continue on, but that's all you have to do with these graphs. So most of the time you just have to look at whatever graph is recommended. That's going to be the graph that pops out over here. Some data is a little bit better or reads a little bit better than the other ones, but that's it. From here, we could just see what the highest year was for, what was it, partisan conflict index. So the figure shows the time series plot. Notice the jump in PCI following the year 2010. So from here, and then a really, really big jump in 2013. During October 2013, the federal government shut down because Congress could not agree on a budget, largely due to the standoff of the Affordable Care Act, aka Obamacare. So that's when we saw a big, huge jump in all of this stuff. And that's it. That's our material for 2.3. If you guys have any questions, let me know. But if not, good luck with your homework.